Okay, so let's go ahead and get started. Another very popular class today. Is that it? The homework days? The class gets a lot more popular? Yeah, that makes sense. Okay, so we did our makeup lecture on Friday last week. The video is actually online, so the video and audio is online on the EE website, not on the webcast thing yet, because the file that was produced was so large we could not send it to the webcast people who were in Dwinell. We had to walk it down to them, and they have to figure out how to convert it into something that I guess is small enough for them to put on the web that you can drive right off the web. But you know, if you get on the EE 140 website, you will find these two files: EE 140 AVI, EE 140 AVI WAVE. The WAVE, of course, is the sound. The AVI is the video for this. So you have this thing, but when you run this thing, you got to be careful, because you're going to get this to start out with. This lasts for about 5 minutes, and I'm told that if you just keep looking at this, it'll crash the thing. So what you need to do is advance it to, say, about this point here. And when you advance it to about, well, when you advance it to some advanced point here, I didn't go far enough, and now I can no longer get that thing. It will behave, and you'll see very nice video. And it's actually better quality than the video that you get off of this webcasting thing. There it is. Well, here. Got to go out here. So if I go out here, see, the video is perfect. It actually looks very nice. Nicer quality than before. The unfortunate thing is that I guess this program could not handle such a large file, so at the end of the lecture I was trying to combine the video and the sound together. Couldn't do it. At least it didn't just dump all of those files to nothingness. At least it gave both files. You have audio and video. I may try this again sometime just to see if it can do it for one of our lectures, because the quality is actually really nice. And you can actually see my mouse on this one here, what I'm pointing to in that sort. Okay, so if you want to watch this video, you can. The lecture notes have been up since Friday. Well, actually, on the web on Monday, but I sent an email around to the whole class, the PDF file, on Friday. So if there's people who did not receive that PDF file on Friday through email from me, you're not on the class email list, and you better let me know so I can put you on the class email list. Okay? But anyway, this is the AVI. Seems to work very nicely here, at least without sound. Yes?
I noticed one thing. The lecture notes, you sent lecture notes via email for, I think it was the lecture.
Yeah.
But the lecture notes online
Do not link to
they link to like lecture 4. The link is just
So lecture 16 is linked to lecture 4?
I think it's lecture 17, but yeah.
No, it's 16.
One of those last two.
Really? Oh, all right. That's a big problem,
we have
actually.
the notes in the email, so
Yeah, okay, that's a big problem, though. But the AVIs are online, right? You guys pick up the AVIs? Oh, yeah, it's not on webcast. It's going to be there at some point, but they're online on the EE 140 site. It's a big file, so it's going to take a while to it's about 5 gigabytes or so. Yes? Huh? Yeah. Oh, the notes don't correspond?
that's what I was just saying. They're linked to a different lecture.
Okay, I'll check that out and make sure that that's not the case, because, yeah, that's a problem. I guess they're on there somewhere, but they're just on the wrong lecture.
You just have to check your email. He has the notes in the email.
No, he's talking about an earlier lecture, though. He's talking about an offset voltage lecture that's not in the right spot.
That's the one I'm talking
Oh,
about.
I thought you were talking about lecture 16.
It's one of the last two.
But I didn't email the lecture 16, the offset voltage one. I only emailed the lecture 16 one, I believe. Okay. Speaking of lecture 16, because that lecture was not on the web maybe early enough for some people, I'm just going to go through it a bit, what we went through. Not take a lot of time to do that. I guess before I do that, let me finish with the announcements for today. Today we're going to talk about compensation and slew rate. It's a first pass through it just to get you past your lab and the questions on compensation and slew rate that you have to answer for lab number 2. We'll go back to it again and cover it in much more detail. We do this every semester that I teach this, a first pass and a second pass. But I just announced about the video and sound of the makeup lecture. They're online. You have the PDF of the notes. Lab number 2, you know, is due the week after spring break, so you still have time to do that. Your midterm exam, you know, is 2 days from now in this very room at this very time. Try to show up early. I'm not sure that the class who's before us gets out early enough for us to just barge right in, but, you know, if you want to barge right in, you probably should, right? So you can at least get a seat. Well, you all get seats, but so that we can start this exam as early as possible. I have too many problems for the exam right now. I have to delete some of them. I'm agonizing which ones to delete. Always ends up being the coolest problem gets deleted. But that's also the meanest problem, too. So maybe you'll like that. Review session, I guess this is leftover from last time. You had your review session last night. I guess they went through the old exam. I had a lot of people in office hours on Monday, too. I have more office hours on Wednesday, 10 to 12. There's some questions about the content of the exam as well. The content of the exam includes everything up to a week before the exam. So it includes what we covered on Friday last week. That's why I want to go a little bit through it. Now, what we covered on Friday last week is not anything incredibly new for you, right? We're basically applying techniques you already know to new problems. That's what we did on Friday. Okay, so even if you didn't see that lecture, you probably still should be able to do the exam because the exam is based on basically techniques we've been learning over many weeks. Okay, so don't worry too much if you weren't at the Friday lecture. You should look at those lecture notes and maybe turn on the sound for the AVI or so. Your homework pretty much covers a lot of what that lecture is talking about. But anyway, on Friday, we sort of continued this. This is actually something we did on Tuesday of last week, this Bodie plot stuff. And on Tuesday of last week, we actually ended up here, where we were handling this non-inverting amplifier, except we were now interested in how it performs with a finite gain. So instead of an infinite gain, it has a finite gain. And when it has this finite gain, what you do is you no longer say that V plus equals V minus. You can no longer say that because it's not an ideal op amp. So what you do is you just use this equation here to relate those two voltages. Right? So the output voltage is going to be equal to V plus minus V minus. If you go ahead and do nodal analysis, taking that into account, we ended up with this expression here. Yes?
Travis said the other day that if you have feedback, V out equals A times V plus minus V minus doesn't hold.
If you have feedback, it doesn't hold? Travis is wrong. Yeah. No, it absolutely holds. At all times it holds. Okay, it's just what happens is V plus and V minus just become V plus minus V minus is a very small number when feedback is there. It can be a very large number when there's no feedback. Okay, but it absolutely always holds. Okay, so in any of your expressions, always you can write V naught equals A times V plus minus V minus. That's the definition of this op amp. Did Travis really say that? Did he really? Oh. Okay. Yeah, I wasn't there, so I don't know what he's saying. But all right, this A is given by this, some finite gain, 1 plus S over omega B. And we end up with this expression here. We then went through looking at this from almost an inspection-like technique, where we sort of equated this circuit to that classic feedback system block diagram that you all know very well, right? And so this now becomes a matter of identifying. In fact, identifying what beta is. What part of this circuit creates beta? And just looking at these circuits, we were able to say that R1 and R2 created beta. And so using that, we can get the transfer function for R1, this R1, R2 branch. That then becomes beta. So beta equals V beta divided by V naught, which is just the voltage divider between those two resistors. And then we just apply that standard feedback system block diagram equation and plug in all the values that correspond to A of S and beta. And so when we do that, we found last time that we ended up with exactly the same expression that you get using the brute force nodal analysis technique, but perhaps we did this a little bit faster by inspection. Okay, and so why did we do this? We did this mainly to underscore the importance of this gain, how high it has to be. And so at this point, we then moved on to talk about, well, we talked about a few things with closed-loop operation, how feedback changes your frequency response. But then we started talking about high-gain op-amps. And we're still talking about high-gain op-amps today, but last time we started taking a look at what's called a telescopic op-amp. And the telescopic op-amp is just combining a number of things that you already know about, which is cascoding, active loads, and differential pairs. So combining all of these things together in order to get a lot more gain. And the reason why this gave us a lot more gain is not because our GMs were larger. Our GMs actually ended up being exactly the same as if I just had two devices right here. The reason why the gain ended up being much larger is because by stacking transistors into this active load here, by also stacking transistors here, I essentially have two cascodes, right? And you know that a cascode gives you enormous output resistance. Okay, so in the end, the gain ends up being related to this output resistance, which required a similar technique to what we'd done before to figure out what that output resistance was. So it's that thing where you drive with a test voltage source, sense the test current going in. You know you have some current going up this way into this cascode network, but you know you also have some current going down this way, which in a small signal sense wraps around and then gets mirrored back out here to the point where you end up seeing a resistance that's just this cascode in parallel with what looks like just that cascode. Yes?
So we did a problem just like this in the review session as well.
Yeah.
And, we have to do that, and it's going to make sure so it doesn't sure. When it loops around and then it mirrors over, does it also go up through the first current mirror and get mirrored over a second time?
You mean this one here?
So
Which?
it loops around,
Yeah.
and then you see two current mirrors in that.
You mean this and this?
Yes.
No, there's only one current mirror, and that's this. So, yeah, that's right.
Yeah.
Oh, I see. Yeah, the review.
Does it mirror twice?
No, it does not in that structure, because when you kind of have to do the impedance analysis on that thing. So I will say, and I said this in office hours too, that problem, I'm not going to say it was unfair. I'm just going to say that it was difficult. It was a very difficult problem. So if you look at that exam, right, and then you're going to see that on this upcoming exam too. There's going to be problems that you're going to be able to just coast through, and then there's going to be that one problem that just, oh my God, where did this come from, right? That's the problem. Okay, so that was that problem. It takes a lot to understand what's going on with that thing. What was going on with that problem? See, this one was not. This one was diode connected. This one was diode connected. This one was not, right? And so in that problem, what you see is a very low impedance on this side here. Okay, this side shows the very high impedance here. So you, in fact, just have a current mirror going from this way to that way. Okay, so it ended up being that, and right, you have to know what the impedance is on this side. And I'll say that everyone that took that exam, virtually everyone that took that exam, said that this was the low impedance, and they were right. But I think all of them guessed, because actually you can't really tell that just from this if that is not diode connected there. But they guessed, they got it all right, and so that's okay. They got other things wrong with that problem, because right, that's kind of that was a nasty problem. You're going to see one like that on this exam too. It's going to be somewhat nasty, but that's the problem that separates. I mean, everyone's going to be able to do lots of the different things, but then there's that one tough problem that I want to see, who can get that and who can't. I do that. I apologize in advance for doing that, but you'll see later on that, when you're finished with this class, you can come back and say, yeah, that's right, I took that exam. And I got that problem too, or maybe not, but I had to face that problem. Okay, so that problem takes a lot, but you have the solutions in front of you, right? And hopefully you can understand the rest of those parts of that solution, right? Okay. Any other questions about that exam or review stuff? I guess you went through the review session. You went through the whole thing. Yeah. This one here. Okay. The source of M2. Oh, down here. Oh yeah, this is a good thing to talk about. So when you look at these differential pairs, you can separate the top part from the bottom part when you think of what's differential and what's not. Okay, so when I say that this is like a virtual ground right here, it is for the input parts, right? When you're doing a differential gain calculation, what are the assumptions when you're doing differential gain? If I say you're going to calculate differential gain, you're automatically making an assumption. And that assumption is you're going to apply +1 here and -1 there. So it's always going to be opposite on both of these, right? If you say that it's always opposite on both of these, then because this really looks like a resistor here, that looks like a resistor there in the T model, right? Because of that, this will be 0. And regardless of what's happening at the top here, okay? So you can think of this bottom part as being fully symmetrical and differential regardless of whether the top is or not. Okay? Now, both the top and this have to be fully differential and symmetric in order for you to divide this into a half circuit. Okay, that's why we don't divide this into a half circuit. But we can still say that the AC small signal voltage here is 0 when you're putting a fully differential signal across those two inputs. Does that make sense? Everyone understands that the AC voltage is 0 here, right? No one's got a hang up thinking, wait a minute, don't you have a VGS dropped across here? Anyone with that hang up? It's reasonable to have that hang up, so if you have it, raise your hand, and then I'll say something about it. Okay. Because right, when we're talking about AC, you don't see the VGS here, you just see a 1/GM resistor there, right? Like in the T model. Okay? So, we analyzed this thing last time. And we ended up with what you might expect us to end up with, a huge output resistance that's now equal to a GM times an R0 squared, right? Whereas before it was R0 squared, just R0s in parallel. Now you have an R0 times a GM times R0. You know GM times R0 is a gain factor. That could be 100 times or something, right? So now you got 100 times more output resistance here than you had in the previous differential pair that we were looking at that did not use cascoded devices. This has got a lot more gain than the previous stage, so that's great, right? We get a lot of gain in one stage. Solve some of our op-amp circuit problems where you want lots of gain, you want it to be a huge gain, but you run into some other problems. Okay, and one of the other problems you run into, I guess we haven't talked about, this is the T model thing that I'm talking about, right? That's why it's 0 here when it's 1 and -1 here. Because you see resistors coming there, and this is just a voltage divider now. If I put +1 here and -1 there, that's going to be 0 across these resistors. Okay? Then last time, okay, we did the frequency response last time, identifying this was the highest impedance node. And the last thing we did was talk about problems and issues. And the problems and issues with this all have to do with the swing of this. So it's great to have such high gain, because we have these huge impedances. But because we had to use so many transistors stacked up, each transistor you use in a stack takes up some of this rail, right? We've got a rail from VDD to ground here. That's the total voltage we have across this. It's supplied by a battery or something. And if we use too many transistors stacked, soon their VOVs or their VGSs added with VOVs will get so large that you barely have any room for an output voltage swing. Okay? If it swings beyond a certain amount, some of these transistors will either shut off or they will go into triode region, which means you lose all of this great gain. And it goes very nonlinear. Okay, so that's the last thing we did. We determined using techniques we had already gone through in other circuits. We determined what the output swing was. We determined the V output max, determined a V output min, and we found that the swing is not very good. Now, we went even beyond this and say, well, in a practical circuit, you're actually going to take an op-amp like this and hook it up in a feedback. And maybe the simplest type of feedback you can think of is this unity gain buffer that you've all seen all the way back in EE40. Well, now you know what this unity gain buffer really looks like, right? It really looks like this circuit with all these transistors, except now you're tying the output to the minus terminal. And so that's what this line is doing here. It's tying the output to the minus terminal. And now you can redo this whole analysis where we're trying to determine the output swing here. And what we determine is that after you do this feedback, your output swing becomes tiny. It becomes this region here. Let's get rid of that for you. So it's sort of a region that's even smaller than a threshold voltage of a transistor. Okay, it ends up being equal to a VT minus an overvoltage. That's about 0.7 minus 0.2 or 0.3, right? So that's from 0.4 to 0.5 volts. That's all the volts you have to swing your signal for this telescopic op-amp. That's a big problem, right? Because we talked about why output swing was so important. Output swing determines how large your signal-to-noise ratio can eventually get, right? Which is a definition of dynamic range in the end. You want to have the largest output swing because you divide that by the minimum voltage you can accept, which is determined by noise. That gives you your output swing, and that's your dynamic range. Okay, dynamic range is an important parameter. If we don't have enough output swing, we can't get good dynamic range. All right, the last thing we talked about here was a problem where the non-dominant pole in this was associated with a mirror node. So if we go back to this, our dominant pole was associated with this output node. The non-dominant pole is associated with a mirror node here, and it turns out that that mirror node pole frequency is not far enough away from the dominant pole frequency to keep things stable. And you don't understand what that means just yet, but I'm about to show you what that means now. Okay, so this is where we left off in the last lecture. We sort of said the solution to a lot of these problems is to not do this, not do mirroring, but actually do what's called a folded cascode type op-amp. Okay, that actually separates this thing from the rest of this. That then allows you to, I guess you could still do mirroring on that, but it separates this from this, that allows you to just drop less voltage across. Well, it opens up more voltage here for you to swing. And you had a question.
Yeah, if you change from VDD, what if you use
Oh yeah, if you increase VDD, you can increase your output swing. Yeah, for all of those things you can increase output swing. However, no, okay, you're right. Yeah, in unity gain you can't. Right, in unity gain it's always going to be that, right? Because that's constrained not by VDD, but by what's happening in here between these, right? So that you're going to have a problem with the unity gain right there. But in general, when you raise VDD, that helps you. But the reason why you can't do that is because nowadays you want to share these analog circuits with the digital. And digital circuit voltages are getting lower and lower by the year. Well, I don't know if they're still getting lower because at some point they can't lower the threshold voltage. So they may be as low as they can get before some kind of genius solves some device problems. Now in the hands of the device physicists to see whether we can keep pushing the VDD down. But I can guarantee you want the VDD as small as possible, at least for transistor circuits. Now, if you want to talk MEMS, you can make that VDD anything you want if you use a MEMS circuit, the microelectromechanical system. So that's why, you know, I'm a biased guy, but MEMS is far superior if it could ever work, right? That's a big if, too. Okay, I'm a biased guy, though, so. All right, so this is... So that was lecture 16. Okay, so now we're going to move on and focus on today's lecture, which is our lecture 17. I really just went through that mainly because that lecture didn't get on the web as fast as I wanted it to, the AVI file and the WAV files. Okay, so I sort of did what I was doing right here. Today we're going to continue high gain op amps, and we're going to talk about compensation for your lab and slew rate quickly for your lab. We just went through all this, the problems and issues with this, and so we ended up here. So one of our solutions to some of these problems that we're seeing, not only the problem with this non-dominant pole being at too low a frequency, but also the problem with the swing not being large enough. One of the solutions to that problem is to use a fully differential, fully balanced op-amp, and we're going to do that later on in the course. But for right now, let me talk about another simpler solution and something that's used quite often and that in many ways you can argue is a superior solution for a lot of different scenarios. And that is to, instead of using a fully telescopic op amp where you're stacking devices, just use more stages of gain. Okay? So go to something like a 2-stage op amp, and this actually is the more classic op amp that people are using. Let's talk about the classic 2-stage op amp. Okay, so that's going to look like something you've seen before. So the first stage of this thing is simply the differential pair that you've seen before that is current mirror loaded. So I'm just going to draw right here a current mirror load differential pair. I'm going to have a current source down here that's supplying the tail current. So I'm going to draw that just as a MOS transistor with some V bias voltage generator that I'm not showing here. This is M1, that's M2, and here's my current mirror active load, M3, M4. And so that's our typical differential pair. That's the thing that, you may complain, oh, that's not enough voltage gain off of that. Here's VDD. And now what I'm going to do is, in order to supply my gain, I'm going to come out here and put another stage here. So I'm going to have a PMOS device here that's actually the driver device. I'm going to go down here to an NMOS device that is a current source load for the driver device that shares its V bias from the same node. So from the same V bias generator there to generate its current. Let me call this M6 and this M7. And this then is going to be my output. And it turns out that in the actual implementation of this is the main circuit that does all of your biasing for you. But it turns out that you have to add a capacitor to this right here that I'm going to call C sub C. And that capacitor is what's called the compensation capacitor. What that capacitor is doing is making sure that this op amp stays stable in certain feedback circuits that it's used in. Okay, that's something we're going to talk about at great length towards the next weeks of this class after spring break. I'm going to say a little bit about it here, just a functional thing that allows you to finish your lab. But it's really after spring break that we'll talk in great detail about compensation. So let me put VSS in here. All right, so this is our op amp, and so someone tell me right now, if this is our op amp, this obviously is our V naught, right? And in an op amp, V naught is equal to some gain factor times V plus minus V minus, right? Whether it's in feedback or not, that's what it is, despite what anyone may have said to you, okay? Now, we're interested in what A naught is, right? And we're interested in what in V plus and V minus. So let me just ask this question. Which is V plus and which is V minus out of these two input terminals? Someone tell me? Where's the plus terminal going to be? Where's the minus terminal on this op amp? 2 is what? Oh, excellent. I've got 2 differing answers on this. So the way you figure that out is you have to start at one of these and then get to the output. Okay, so if I start at this one here and I go from here to here, what's the sign of that gain from here to here? It's positive, right? But then I'm going here. This is now a common source stage, right? This is gain from the gate to the drain. What's the sign of this? Is negative, right? So if I start here and get to the output, that's negative. So that's why this is the negative terminal. Okay, and you can do the exact same thing on this side. If I go from here to here, that's negative. But then there's another negative there which makes it positive. So this is the positive terminal. Okay? So that's a skill you ought to have. When you see a big op amp circuit like this, you should be able to say which is the positive, which is the negative terminal. Okay? Now obviously the other skill you should have is to be able to calculate the gain of this thing. And at least write the equations for the gain. And on the exam, right, when you're given a problem like that first problem on the midterm example that you have there, Be as complete as possible in writing out your gain equations, okay? So this is a situation where you're just writing out gain and you're not calculating anything, right? If you're writing out gain and not calculating anything, be as complete as possible. Include the little R naughts, include those things. Or if you neglect them, you've got to write something saying neglected R naught or something like that, right? Make it very clear what you're doing, right? If you're calculating something, you can neglect anything you damn well please, and we're fine with that as long as you're within 10%, right? But then you have to calculate, right? So which one takes the more time? You tell me, right? Okay, but some of them will be calculate, some of them will be just like the first midterm where you just write the equations down. And when you write those equations down, we give points for every little thing you put in there. Okay, so let's say there's an equation GM times RC parallel with R naught. There's points for GM, and there's points for RC parallel R naught. Okay? So just writing something down will get you something, okay? Don't ever leave something blank, right? Because you may get something out of it. So just write something down. All right, so back to this. Let's get the gain of this thing, and we're going to get the gain the same way that we've always done it. Okay? And so we're going to do it stage by stage. Let's get the first stage gain. Meaning I want the gain up to this node here, which is node 1. Okay? I want the gain from the input, these two inputs to node 1 here. And first stage I'll call AV1. Say that's V1 over V sub I. And I guess if I'm going to say V sub I could treat this fully differentially, or I can do the other thing that I usually do, which is say ground this and put a V sub I right there. So I'll just do it that way this time. And if I do that, what is that gain? You should just be able to tell me now what that is. Especially 2 days before the exam, you should be able to tell me. Oh, come on. Is it negative or positive? Gain from, say, here to there? We just said what it was. Yeah, so this is going to be positive. Maybe it's a GM1 or 2. I'll just choose GM1, right? And so the resistors are going to be RO4 and RO2. Right, and RO2, you know, it's doing that thing where the current's going around and it's getting mirrored back. That's why it's just RO2. Okay, so RO2 parallel RO4 there. So that's my first stage gain. And my second stage gain AV2, that's going to be from V1 to V0. That's just the gain from here to here. Okay, usually you take into account loading, but it's MOS, so there's no loading, right? I have an infinite impedance looking into M6. So this now just becomes minus GM6 times a parallel combination of the output resistances of M6 and M7. So R06 parallel with R07. And that's it. So I could just determine the gain is just AV1 times AV2. That becomes GM2 times R02 parallel R04 times GM6 times R06 parallel R07. I guess I have a negative sign in front of that whole thing there, but that's the gain of this thing. And so what do we find about this gain? We find that this gain is the same as the gain of that telescopic op-amp. Right? So if you go back to those notes with the telescopic op-amp, this is exactly the same gain equation for that. So we get an equal amount of gain, and but we just do it in 2 stages here. Okay, but what are the advantages of this? Why is it that this is better than the other one? This is better to a good measure because of output swing. So now look at what the output is. The output's no longer any part of this. This is actually a very small voltage, which you know because you got a lot of gain across this stage. If there's a lot of gain across the second stage, this voltage is going to be small. Okay, so that voltage is going to get nowhere near your VDD and VSS. It's not going to control your output swing. It's this voltage here, which is your actual output voltage. It's going to be able to swing, but now look how far it can swing. right? It doesn't have two stacked devices up here. It doesn't have a current source and an input device and maybe another stacked device there. It's just got one device between it and VDD and one device between it and VSS. So I can very quickly write out my output swing voltage, V output swing. That's just going to be VDD minus VSS, which is the total amount of voltage that I have available to swing, but now minus the overdrive voltage of device 6, which I'm putting in absolute values because it's a PMOS device, minus the overdrive voltage of device 7, and that's it. Okay? This has a lot of output swing, so it has very good dynamic range. Okay, so comparing that telescopic design to this design is superior in its output swing and dynamic range abilities. Okay? Turns out that the telescopic actually does a better job when we start looking at frequency response for things like settling times or so, but that's sort of the second half of the course. So each of them is useful in its own right for different applications, but if you want to output swing, this two-stage op-amp is the better choice. Okay? Now, there's another thing now that I want to talk about here, and that is the frequency response of this and why certain aspects of frequency response are important. So, in particular, why C sub C is required. So let's talk about that for a second. And this is just going to be a first pass through this, just to help you get through your lab right now, which comes a little earlier than the lecture on compensation. Okay? So, the frequency response of this thing you know is going to look something like this. You know that you're going to come out here and you can calculate where its dominant pole is. And where that dominant pole is, I'll just call omega P1. That's something you know how to calculate already for this thing. Do you know how to calculate that? Let's do it. Okay, so let's get the dominant pole here. So omega H is something you've calculated many times. But what's that going to be in this case? Can you tell me which node here is going to dominate the frequency response of this whole thing? Yeah, the output is a potential contender there. I'll agree with that.
How big is CC?
CC is usually a pretty good sized capacitor. So it could be a picofarad or something like that, more than that. On your lab, it's huge. But CC is a good size. Okay, and so you really have two choices here, right? What you're looking for are the high impedance nodes. You know this is a low impedance node, so you're going to forget about this one, right? This is a high impedance node right here. This is another high impedance node. They're about the same impedance, right? So which one will dominate the frequency response? Yes. Exactly. So this C sub C, right, is tied between a gate and a drain with a lot of gain across it. So you got the Miller effect going on in a big way. This C sub C is going to Miller effect into some C Miller capacitor right here. That C sub C turns into that Miller capacitor, and that Miller capacitor is enormous. Okay? And so I can now just write down what this is going to be. It's going to be the resistance at that node, which is R02, parallel with R04, times the Miller capacitance value of this thing, which ends up being then 1 plus the gain of that second stage, which is GM6 times R out 6 parallel R out 7 times C sub C. 1 over that. That essentially is my dominant pole. Now I have a lot of nodes in this thing with a lot of other capacitors, but all these other nodes don't have nearly as much capacitance, and only one other node has a similar resistance, but it has much less capacitance than this one. So notice what I just did. I just neglected everything but this one and saved myself tons of time because I know this is the biggest time constant. Okay? There's an approximation you want to use. And you could do this on the exam too. You just say, You know, you don't have to write out the rest of this. You can just write something, and all the rest are neglectable. Okay? Yeah. Yeah, see? Oh, yeah. So what I'm assuming is C sub C is fairly large here. So it's larger than all those capacitors, I'll say. So let me write that down. Much greater than device caps. Okay? All right? Yes. RO at node 1? Why would I get RO6 and RO7? That's the gain of the second stage. So this is the Miller effect. So this thing right here, that's the value of what I wrote as CM. Okay. Okay? So that's the frequency response of this. So that's great. We have now determined this frequency right here, which I'm calling omega H. I guess I'll also call that omega P1, since that's what I'm calling it in this chart right here. Okay, it turns out that if you want a stable circuit in negative feedback, okay, and this is just, right now I'm going to give it to you as a rule of thumb, but this is actually going to be something very concrete later on in this course. This is going to be the rule of everything that you do in terms of having a stable feedback circuit with an op-amp, but you know this is going to come down. But you know that it's not going to go down forever at that 20 dB per decade. Sooner or later, you're going to hit another pole. Maybe it's right here. That's where the second pole will be. And in this circuit, it's probably going to come from around here. Okay, much less resistance. Or it could come from around here. Okay, but probably here for reasons that I'll talk about later on. Right, much less resistance, smaller capacitance, so a much higher frequency. This is orders of magnitude. This is a log scale here. It's a Bode plot I'm trying to show. So that's log omega, and the units on this scale are dBs, decibels. Okay, so that's quite a bit of distance there, but nevertheless, you're going to get this, and once you hit that pole, it's going to start going down even faster. Right, so this is your 20 dB per decade. And here, if it looks like this is going to be your 40 dB per decade at that point. All right? Now, the interesting thing, the takeaway that I want to give you right now is that this distance right here between the locations of these two poles, that decides whether a feedback circuit is stable or not. Okay? So that's important enough that I'm going to write that out here. So that distance decides whether or not a feedback circuit using this op-amp is stable or not. Okay, that distance makes a big difference. Okay, you essentially have to make sure that this distance is big enough. And it depends on what gain you're trying to implement with your feedback. And so I think I'll just leave it at that. You want this distance to be big. Okay? And so that's why this compensation capacitor C sub C is here. Because without this C sub C, maybe you end up with this. But when you put C sub C in, what C sub C does is it takes your non-dominant pole, your first pole, omega P1, and sends it to an even lower frequency. Okay? So the action of C sub C, if I put it in green here, when I add C sub C, that takes that pole and brings everything down and maybe brings the pole to here. So that's omega P1 with C sub C. And when you bring that pole there, now what happens? Now what happens is you still have this 20 dB per decade happening from that starting point. I may be more accurate about that. So you got 20 dB per decade here, same slope as that. It goes all the way out here. Then it hits that pole. Then it starts going down like that. But now what you see is that you have increased this distance. increase that distance, and so things are more stable in feedback. Okay? Yes,
That's right. It seems like it would be decreasing your bandwidth.
you are.
I thought with negative like with feedback, generally completely increases bandwidth.
You do. So in the end, this is the open loop op amp response right now. So we actually have not applied feedback to this yet.
Okay.
We're just changing the open loop response. And then when we do apply feedback, I'll be able to draw a line across here, and then it'll follow the green line. You see that? But everything I'm talking about here is open loop. Okay? The open loop op amp, you want the first pole and the second pole to be as far apart as possible in order to get the best stability. And so I'm not telling you how far apart. We're going to talk about that in several lectures after spring break. But right now I just want to give you that concept there. And why am I giving you that concept? I'm giving you that concept because you're going to need this concept when you look at your lab. So let's take a look at some of your lab circuits now. You saw that I had one to steal, so I'm going to steal it right now. This circuit. Okay, so this is your lab op amp here, and it is a two-stage bipolar op amp. And just to make sure you recognize it, it's your lab. Okay? First thing I guess we ought to do is just point out things you probably already know about your lab. Right? You can recognize a lot of different parts of this thing. You pretty much understand how this whole thing works now, right? And so just to point out some of the obvious things, if you look at this right here, what is this? Yeah, you can call it either a current source, but I like to call it a V-bias generator. Because what it's doing is it's providing that voltage V-bias that then is used for all the actual current sources that you have in this circuit. Okay? So that's your V-bias generator. And I could keep looking at different things. It's obvious what this thing is right here. That thing is your differential input stage. So it's your first gain stage. Let me give myself more space to do things here. Okay? And then I can look at the bottom of this thing here. If that thing to the left is a V-bias generator, this thing right here is a current source. Okay? So that single current source is supplying the op-amp differential pair tail current. That supplies the op-amp diff pair tail current. And so obviously this thing here is yet another current source. But this is now serving as the active load for this stage right here, which is a degenerated common emitter amplifier. So it's a current source for, well, let me be more specific. Call it active load. For the Q6 degenerated common emitter amplifier. And so I should point that out too, right? This whole thing right here is what I just said. It's an emitter degenerated common emitter amplifier. So that's our second gain stage in this. And then finally, this thing at the output right here, that's an output stage. Something we haven't talked about at great length yet, but something you can already understand given your small signal and DC bias point abilities. And so, obviously from the name here, this output stage is there to drive small resistive loads. Okay, and that basically is your lab op-amp. This is what you've put together, and it's incredible that you can get a functioning circuit like this on a breadboard, but you are. And it actually is performing to give a certain amount of gain. And what it's really doing is teaching you all sorts of concepts about op-amp design. So let me give a few remarks about your lab here. And to do that, since I don't want to be writing too much, I'm just going to steal them here, as is very common for me to do these days for some reason. Okay, but here's some remarks. So you analyze this in lab number 2, so you all can recognize it. Usually, the resistively loaded differential pair, right, with these two resistors there, usually you put a current mirror there instead, right? You replace that with an active current mirror. So why is it you aren't doing that in your lab right now? It's because you're implementing this on a breadboard. So if you implement this on a breadboard, if you use an active current mirror here, you would generate such a large impedance right here, such a large resistance, that the breadboard capacitance would be too much for it. And the 3 dB bandwidth of this thing is just going to be too small. Okay, so that's why you're not using an active current mirror for this. You're just using these two resistors there. But that is a design all in itself, right? It actually allows you to achieve a reasonable amount of gain in this first stage. Okay, other thing to recognize here is that RE6, this resistor right here, which I guess I'll label RE6, that's emitter degeneration for this second stage Q6. Why are we doing this? Why do we emitter degenerate this second stage? I mean, isn't that just hurting our gain? Okay, that's part of it, yeah. But that's not entirely it. Yeah, that's just what was said. So larger swing is one, the larger input, larger range of inputs is what it does. Less, yeah. So there's, okay, a lot of good answers here, but yeah. Oh, that's part of the larger swing there. A lot of good answers. All these are valid answers. I was looking for it increases your input impedance for this, so it doesn't load this as much. But all your answers are just as good as mine. Okay? So part of it there is, it raises the input resistance of Q6, right? Plus it helps with biasing in the end. So this thing, it's easier to bias this up if it has this resistor there, because you want a certain voltage coming off of this here. And you can't drop, if you didn't have that resistor there, you'd have to drop 0.7 volts across this resistor here. Right? But now that you put that resistor there, now you can drop anything you want there, and you can make this output whatever you want. Okay? So there's multiple reasons why that resistor is actually there. You see the same kind of thing in the output stage that I have here, right? So these resistors, this resistor and that resistor, they're also there in order to help with biasing and to increase the input resistance of these two transistors. Now this output stage is kind of a funky looking thing, right? So what's going on with this output stage here? What's happening here, first of all, what's this output stage supposed to do? You want it to drive small loads. Okay, so in other words, you're going to have a next stage coming after this that's probably going to have some transistor input there. Or not, right? But it's going to present some kind of input resistance to this whole circuit. And so what do you know about voltage amplifiers, which is sort of what an op-amp is? It's a voltage amplifier. What's the ideal output resistance for a voltage amplifier? Should be 0, very small. Okay? If I took this as just my output, what's that resistance? Yeah, I was just looking for large. But you can write it out, right? The RO times 1 plus GM times this R, etc., right? But that's a very large resistance. And so that means that this stage in itself does not make for a good driver stage, right? Because if I take a large resistance and then I try to drive a small resistance in shunt with that, that voltage divider is going to kill our gain, right? And so that's what this is all for. That's a large resistance, but because I'm using this resistor and that resistance looking in is even larger. So it's even larger than that resistance. And so now I'm driving that driver stage without losing the gain from this second stage, because the driver stage resistance is not loading this stage. But now look at the driver stage. Look what it is. It's this clever way of, it's not an inverter, right? It's kind of the opposite of an inverter, because I've got my emitters on the insides here, right? With the emitters on the insides, what this is doing is it's presenting a very small resistance looking that way, about a 1 over GM and a 1 over GM that way. And this transistor at the top will be used to pull voltages up. This transistor at the bottom is used to pull voltages down. Yeah, it is a push-pull circuit. And so we'll talk about that in a second by the end of this lecture here. But that's what's happening there. The main thing with this is you're trying to get a very low output impedance that then allows you to drive all sorts of other output impedances here. Okay? So that's what's happening with the output stage in that lab design that you have. And now what I really want to focus on, though, is that compensation capacitor. So let's repeat this. Do I have enough space here? This will be an exercise in what I can fit. Yep. All right. So now it comes down to the compensation problem with your lab. So in your lab, what you're asked to do is compensate this amplifier by using this C sub C. Okay? And now we just talked about a C sub C with a previous example that I just gave, which is this one here. That's our C sub C, right? And what C sub C does is it's placed specifically in a path with large gain across it. Okay? And if I have large gain across this, I can make C sub C look a lot bigger because it gets Miller multiplied. All right? So if you look in your lab, that's where its C sub C is situated. Right? This second stage has a considerable amount of gain. Even though it's degenerated, it has a considerable amount of gain. And so what you're trying to do with this C sub C is put that pole frequency, the first pole frequency, in a slot where it's significantly distant from the second pole. Okay? Now, it turns out that in this op-amp, this capacitor is also doing that same function. Okay, so that's what this 680 picofarads is for. That 680 picofarads just tries to brute force it. It takes the large impedance from this node right here and combines it with a capacitor to create this compensated 3 dB frequency, okay, which is lower than what, of course, the op-amp would have without this capacitor. What your lab asks you to do specifically is take this, which is already a compensation capacitor. I'll call it the initial compensation capacitor. Okay, so you want to take that capacitor and you want to replace it with this. Okay, so the lab asks you, I'll just say specifically here, in your lab, you are to replace this with this right there. Okay? And the reason why we want you to do this is because this capacitor should end up being a lot smaller than that one. They're all doing the same function, but instead of putting the capacitor here, if you put it here, you're going to be able to use a much smaller capacitor. And when you have an integrated circuit, that's a huge difference there. Even for the off-chip, that 680 picofarads probably isn't that small a capacitor. But in the end, what you need to do in your lab, and I'm telling you this explicitly because this is just a pass-through and compensation. We're going to do a lot more detail in several weeks after spring break. In your lab, you need to simply choose C sub C so that it generates the same frequency, 3 dB frequency, which I've been calling omega P1 as the original C equals 680 picofarad capacitor. Okay? And again, all of this is for stability that we'll learn about later. Okay, is that clear? What we're trying to do? And that's all related with keeping omega, let me say that, all related to keeping omega P1 and omega P2 I don't want to say, let me say as far apart as needed. For stability. Yes. Mm-hmm. Yeah, you're right, actually. It depends on what the gain is across this Q6 here, because that gain can be a pretty significant factor. So it's not going to be as small as it could be, this C sub C. You're right. If this had an active load here, if this had a current mirror load with a much larger resistance, this would be extremely small compared to that 680. So as a consequence, I think it's going to be smaller, but it's not going to be 1 picofarad or so, right? It still may be a significant number there. Okay? But usually that's what you're doing. That's why you're putting the competition capacitor there. You want to put a lot of gain across this stage, and you would have that large resistance, which you point out correctly we don't have right now. Okay? Yeah, good recognition there. Okay? All right, so that's your lab. Now there's one more thing that I need to talk about for your lab, and let's see to what degree. Yeah, good. I set myself up to cheat a little bit with this slew rate thing. But the one more thing that we need to talk about is slew rate. Okay, and I'm cheating a little bit on this because these are things that I think you've seen before in now your 20N type classes. Okay? And that is, slew rate is an important thing in your op amps. So what is slew rate? So if we look at this op amp here, this is an op amp that's hooked up in a unity gain feedback. And if I go ahead and I put an input signal into this that looks like this, where it just shoots up, it's a square wave, just a single step response input to this thing, then how do you expect this op amp to respond? Okay, so you know how to do this from your 20N type courses, right? This is your Laplace transforms, Fourier transforms, right? 20N? No Laplace transforms? No? Fourier transforms? Okay, Fourier is good enough too, right? Laplace transforms just differ only in that we're using S instead of the j omega there. There's other differences too, but they're essentially the same concepts here. It's frequency domain versus time domain. Okay, so I've got this in Laplace here, Laplace transform theory. But basically, the easiest way to solve this problem is just to represent the transfer function of this, which we already do anyway. When we derive the transfer function of our op-amps, we're basically deriving a Laplace transform based transfer function. So the transfer function, say V naught over Vi, could be 1 over 1 plus S over omega 1, where omega 1 is, we're assuming, a single dominant pole. Okay? I can also write this as 1 over 1 plus S times tau 1, where tau 1 is the time constant equal to 1 over omega 1. All right? Now, in Laplace transform theory, a step input is equal to the amplitude of that input, which is V sub A, times 1 over S. Okay? So very similar to the Fourier transform step input as well. Right? And then in order to process this input through this transfer function, I merely multiply this by the transfer function value. So that's what I'm doing right here. To get my output voltage in the frequency domain, V naught of S, that's V sub A over S times all of this stuff. I can factor these two out, okay, and then do an inverse Laplace transform, which then gives me an output voltage in the time domain that's equal to V sub A times 1 minus e to the minus t over tau 1. Okay? Now this at least should be familiar to you. Okay? I got to this result using Laplace transforms because to me that's just the easiest way to do it. But you can also do it using full-blown circuit theory, nodal analysis, putting in the integrals, etc., and you'll end up with this, right? At least this you're familiar with, right? The response to a square wave of something with a single pole should be this type of exponential, 1 minus this exponential here. So in the end, this should be a familiar sight. Okay? And so I've got a couple other things here. This is in this buffer circuit here, if this black is the open loop op-amp response, then the red here is the closed loop response once I hook it into the buffer circuit response. Right? Once I hook it into this, it becomes unity gain. Unity gain is 0 dB, so I stretch this across. I get a new 3 dB frequency that's omega 1 here. Okay? We sort of talked about this in the last lecture too, how we do this. Now, why am I going through all this? Because this is all stuff that you probably know already. Put a step function into a single pole transfer function, you're going to get this 1 minus the exponential response. The reason why I'm telling you this is because if you try this in the lab with a given op-amp, sometimes you will not see this. Sometimes instead, you will see this. Okay, and so the question becomes, well, why is it that we see this instead of that with an op-amp? Okay, and the reason for this has to do with how much current your output, your op-amp can actually source. Okay, you'll always see this if your op-amp can source an infinite amount of current to supply, to charge up whatever capacitance there is in this system. Okay, but if it can't, it's going to do the best it can, and the best it can is going to be a linear increase here. Okay, let's go deeper into this and answer why it is this is the case. Okay, so first of all, the reason for this, I'll just write down here, is that the first or second stage of an op-amp cannot source enough current to mimic the shape, or mimic the slope, or speed. Same thing. The slope in time is speed here, of a fast rising signal. Okay? So let's take a look at this in terms of op-amp terms. Let me draw a little op-amp here, and just to show you things from the other side, I'm going to make this one with PMOS inputs. So here's my diff pair with the PMOS input devices. I'm still going to have a current source load. The current source will have NMOS devices. Okay, and so I'm going to have a second stage of this, but I'm just going to draw my second stage in some shorthand here. I'm just going to say the second stage is some amplifier here, which it could be exactly the same as what we just drew last time. So that second stage is just shorthand for this thing right here. So it's shorthand for this thing right here. Oh, what a great reminder for me. This is your homework number 6 coming back to you. I think there's still 15 minutes, well, maybe less than 15 minutes left. And this is your homework number 5. Okay, so all of it's graded. You should have all of the homework solutions online. There were some emails about the last page for homework number 5 missing. And I saw another email that looked like it resolved that, but actually I think the last page is still missing. So that should be up on the web probably sometime today or so. Yeah.
Will the homework we're turning in today be
No.
solutions be up soon?
Those solutions, yeah. I guess those solutions have to be up today. So we'll get those up as soon as possible as well. But just to finish this thing here, so this thing represents that second stage there. And let me give it an A2 to say that it's second stage gain. And you know the second stage has this capacitor across it. That's C sub C. So I can draw that whole op-amp circuit in sort of this simplified fashion that I've shown right here. Except this one is a PMOS input. The other one is NMOS. So that's M1, M2, M3, M4. Okay. So I'm hooking this up into unity gain feedback, but I don't have to really address the unity gain feedback right now. What I want to address is what happens to the currents in this when I apply an input to it. Okay, so let's apply an input to this. And let me give myself some space to apply an input. All right, so I'm going to ground this out here. And I'm going to apply my input V sub I to that transistor. And again, that input V sub I is going to look like the input I just wrote here. It's going to be something that's just a step function. It's going to go from a very small voltage to all of a sudden a very large voltage. Okay? In that case, what happens to this thing here? Okay? What's going to happen is suddenly as its voltage goes up, what happens to this transistor? Not sure? It's PMOS input, so it's a little bit tricky. But it shuts off, right? So suddenly I put a large voltage into that transistor. This transistor goes off. M2 goes off, right? Which means that the current coming out of M2 is 0. Right? And so when the current coming out of M2 is 0, that means all of this current, which I'm going to say is equal to 2 times I1, okay, where I1 would be normally the currents going through each of the transistors. Right? So this is 2 times I1. All of this current now goes through this transistor, which is on. So that transistor is on. 2I1 goes down that transistor. As you know, it keeps going down into this mirror, and it's mirrored out here. Right? So I get a mirroring of 2I1 here. That's mirrored current. And then that 2I1 sucking down can suck charge out of that capacitance. Okay? But you'll notice that that 2I1, that's all the current we've got. We can't source more than 2I1. Right? There's no way we can do that. This is a current source here. If this is an ideal current source, it only sources 2I1. And you control how much of that 2I1 gets to the output by controlling which one of these devices is on or off. right? And if you go all the way and shut this device off, keep this guy completely on, that then puts all the 2I1 through here. It takes all the 2I1 out there. That's all the current we've got to take out of this capacitor right here. And of course, the charge across that capacitor determines what that output voltage is. Right? I can write the expression for this output voltage as equal to 1 over C sub C times the integral of the current that's charging that capacitor, which in our case is a maximum of 2I1, and that times dt. Okay? So what does this tell us? This tells us that if the maximum current we can deliver here is 2I1, then the slope of this line right here cannot be faster than dV naught dt, which is what I'm going to call my slew rate. So the definition right here, slew rate, SR, is equal to the derivative of the output voltage with respect to time. And looking at this equation here with the integral, that's just equal to 2I1 over C sub C. Okay? And that's a definition here for slew rate. So on your lab, when you see slew rate, this is what we're talking about. We're talking about the fact that you cannot source enough current out of your lab amplifier to charge up this capacitor fast enough. And as a consequence, what you see in your lab is something like this. So if you apply a very fast and so fast can mean two things. It can mean that the signal is high frequency, but it could also mean that the signal has a large amplitude. Right? Both of those things can cause a very large slope, especially when the sinusoid is going through zero. So if I apply a sinusoid that's very fast, then this is what you're going to end up seeing. So this is time. This is your output voltage. Okay, this is your expected output voltage, which is going to be a sinusoid. But this now is actually what you see. Okay, this slope here is too large. So say that slope of the actual output waveform you're trying to see, say that's greater than your slew rate. If that slope is greater than the slew rate, then instead of seeing that sinusoid, you're going to see the maximum slope that your amplifier can put out. And that's what that straight line is going to be. This is going to have a slope equal to your slew rate. Okay? And then once it's hit this point here, the slope of the output is no longer larger than the slew rate. So now you can follow this sinusoid. Okay? And you can follow it down. Well, actually, no, that's not true. That's wrong. Let me undo that. So you're not going to follow that sinusoid because the slope there is still faster than the slew rate. It's just in the other direction. Okay? So if the slope now is in the other direction, what's going to happen is you're going to go as fast as your slew rate until you hit that point. Okay? And then you're going to go as fast as your slew rate until you go back up there. So instead of seeing a sinusoidal waveform, you're going to see a triangular waveform. And that's all due to slewing. Okay? And so you need to be able to recognize this in your lab amplifier. So in this thing right here, if I copy that and paste it here, you need to recognize the components here that can cause slewing. Okay, so this is your current source right here for that op amp. right? If this current source is putting out a certain amount of current, right, then it's going to dictate the maximum current that you can feed into that capacitor right here. And that's what's going to cause the slewing of your lab op-amp. Okay? So the reason why I want to get this done here is because your lab is due after spring break. We don't have another lecture here, but I've pretty much done it here. Okay, so you have everything now that you need to finish your lab. Okay, you have the slew rate concept here, and you have the compensation concept. You should be able to finish your lab now, but that's probably not the top thing on your mind. Probably it's that exam that occurs on Thursday. So I will see you then. I'll be here earlier than the class to see if it's even possible to get an earlier start. So try to get here as early as possible.